Let's talk about Newton's method for systems. So far we talked about one equation, one unknown, and now we talk about a system of equations. 5 equations, 5 unknowns. So far we talked about 2 problems, GPS and a robot, and we showed this might be the origin of such a system. And now we talk about there's a given system of equations, n unknowns and n equations. This number must match in this section. And we are looking for the root of such a system. Every system of equations can be rewritten, bring the right hand side to the left, as a is equal to 0 problem. Okay, and here we see an example, a very easy example. We have 2 unknowns, x1 and x2, and we have 2 equations. This number matches. Here we have an equation equal to 0. That means we can define a function taking 2 input arguments, x1 and x2, and output also 2 output values, so output vector. So this is the first coordinate of the vector, and this is the second coordinate of the output vector. And what can we do? We can examine the Newton method for one equation and one unknown, and it's of that type. And then we can manipulate this iteration and come to a suggestion how an algorithm for more than one equation might work. So rearrange in the following, bring that to the left hand side, then you have this is equal to that. That can be written as the inverse of f prime times f of x. So you can rewrite that way, and thus you can, instead of the inverse, write as this equation which has to be solved. Okay, and having this in mind, you can formulate the following. Write f prime. This is not mathematical standard notation, I know that, but maybe for the standard student it helps to better understand the meaning. Normal mathematical notation is a little different, and it's the Jacobi matrix we will see in an example, or better in 2 examples. And then we have a linear system of equations. Notice we want to solve a nonlinear system, and what we are using as the key to finding the solution is a linear solver. And then we find the solution x for that, and then we iterate. We come from xn to a new xn plus 1. That's the doing. Okay, we have xn and it's updated by that, and we find that x as the solution of that equation. Okay, that's not so easy to understand, so let's check our example. If this is our f and we have some starting point, somebody has to provide this starting point. Okay, -1, 0 is it. The Jacobian is the derivative in respect of x1 is 2 times x1 plus 0 minus 0. So only 2 times x1. The derivative of that in respect of x2, forget that, it's 2 times x2. And then the derivative of that in respect of x1 is e to the power of x1, and the derivative in respect of x2, doesn't matter, -1. This is the Jacobian for the general point x1, x2. And now next we will be interested in the Jacobian in this specific point. And we need the function value. Okay, so -1, 0, -1, this is the -2. 2 times 0 is a 0. E to the power of -1 is 1 divided by e. And -1 is -1. So this is the Jacobian at that point. We need the function value, and here we take -1, -1 squared is +1, plus 0 squared -1 is this 0. And then minus 1e to the power of -1 is 1 divided by e, and -0 is 1 divided by e, and the -1 will be a -1. So this is the Jacobian for every point x1, x2, and this is the Jacobian of the specific point -1, 0, and these are numbers. 1 divided by e is 0.3. Okay, and now we solve that problem. Take the Jacobian, take the function value, take the negative of this function value, and then find x such that this equation is satisfied. How can we do? In this case, there's more than one possibility, but normal process, take the inverse for two equations and two unknowns. A linear system is most effectively solved by the matrix formulation and then taking the inverse. The inverse for 2 by 2 matrix is very easy to find. For 3 by 3 it's no more easy, but for matrices of size 2 by 2 it is very easy. So take the inverse from the left and then it vanishes here and it shows up on the right hand side. So what is the inverse? It's swap the elements on the diagonal, take the negative value on the non-diagonal, and then one more thing, don't forget 1 divided by the determinant. -2 times -1 is 2, -0 times something is 0, so 2 minus 0 is a 2, a half, and then copy that also, and now do this multiplication and then multiply by a half, and you get the desired x solution. And in this case this solution is this one, 0, 1 divided by e. Multiply that and multiply by a half, and you get this one. And then update x0 by this x by adding them, and adding them you get that -1, and 1 divided by e is more or less 0.3 or better 0.3679. This is our new point, our updated point. And if you iterate that process, you can do that by your own as an exercise, as a possibility to train. Then you will get these values. Unfortunately, these Jacobian will be some numbers, not -2 and 0, but some fancy numbers. But in the end, this should be your next x2, and please do these calculations. A second example to also train you is the following. Find the solution for that system. You have to provide some initial starting point, and let's use 0, 0 as this initial starting point. And now what will you do? Please think about. Okay, the first step is we need to reformulate, because we can only search roots. So we have to reformulate and bring the right hand side to the left by a minus or by a plus. So we are here. What is the next step? View that as a function f of x, y. And what kind of function did we define? We defined a function getting input, two variables x and y, and producing output two variables 1 and 2. What do we need next? Jacobian for the general x, and then Jacobian at our specific starting point and the function value. So please do the calculations. Okay, that's what we want. And the Jacobian is, what is the Jacobian? What's the correct answer here? The correct answer is that, and so on. So this is the derivative. This is the derivative of that with respect of x. This is the derivative of that with respect of y, and so on. What do we need next? We need to know what's our initial starting point, and then we evaluate this Jacobian at 0.00, and we get this matrix. And we need the function value at the 0.00, and this is 2, 3. I hope you can do all these calculations and find the correct answer. Then we have to solve this problem. Take this Jacobian, take this function value, but the negative of this function value, and then solve that system. And the best way is to multiply with the inverse from the left. And then you get the following. And is that correct? Or is something missing? There is something missing. What is missing? 1 divided by the determinant of this matrix, and this is -1 times -0.69 minus 2 times 0. So okay, this is correct now. Then multiply and use electronic help in this case. And so this is our x, and now we update x0 by doing what? Adding x0 and our x. Okay, adding them, we get the following. We get 1.99 and 10.1 in the second coordinate. Please don't forget that. In this case, if you forget, it doesn't matter, but the next time it will matter. Okay, so this is our second example, and I hope you was able to do every step by yourself. Okay, what are the advantages and what are the disadvantages of this idea? We have quadratic convergence, how mathematicians can show. I tell you it's quadratic convergent, but I don't tell you why. Please believe it. As long as the Jacobian is invertible is the corresponding thing to being not zero. In one variable we have the formulation if the derivative is non-zero, and non-zero means there is an inverse, a multiplicative inverse, and so there's also this analogy. Okay, what is a very big thing, and it's sometimes mentioned, but without emphasizing it very much, I always emphasize there must be some starting initial value, and this must be provided by someone, and the someone is the user of the algorithm, and that's a disadvantage. But this disadvantage does not vanish, unfortunately. If you have hope there will be an algorithm free of that restriction, I must disappoint you. This is possible for specific subclasses such as polynomial systems of equations. That was part of my PhD thesis, or this was my PhD thesis, to talk about polynomial systems, and there's no need to provide some initial value, okay? But normally the user has to provide only one root, or better at most one root corresponding to the initial value may be found, never more than one. If you want, if there are more than one solution, then the user has to provide two appropriate starting points which are more or less close to the solutions you are looking for, and that's a restriction nobody likes. It's a dramatic restriction, unfortunately. And for using that algorithm, the user has to provide the Jacobi matrix, the derivatives, and that's in practice a very big disadvantage which has to be overcome, okay? But in this section, okay, we need a derivative, and in this section it was no problem. This is the code, the MATLAB code, and for me this is a miracle, because we talk about systems and the code is so close to the one-dimensional code that it's unbelievable that this code works also for systems, but it works indeed, okay? The one-dimensional code would use absolute value, and here we have to use norm, the Euclidean norm, okay? And all the rest is more or less unmodified. I think it's completely unmodified. And for the MATLAB syntax, you can call this algorithm, this function, with a code like that. Okay, and we saw how it works. We saw two examples, but what is the reason, the mathematical reason it really works? I am a mathematician. I am not satisfied about the explanation. There is the one-dimensional Newton's method, and now we play around with some inverse of prime of x and so on. And so I want to learn the exact reason, and that's what I want to talk here now in the end of that subsection, okay? And for me this is a very, very nice explanation, and I'm desperately need a detailed explanation. Okay, if this is our equation, our system of equations, we can view that as a function taking two inputs, producing one output, and then we can visualize functions of multivariate input variables, okay? And then we can visualize this function here, and we can visualize the function only close to the initial starting point. So what can we do? Instead of taking the function, we can take the tangent plane and work with that tangent plane, and that's the basic idea. So how can we get this tangent plane? We need the derivatives, we need the derivatives at this specific point. And then we get these four partial derivatives for our example. And the next is, that's the tangent plane for the first function, that's the tangent plane for the second function, and now we are looking for the roots of that tangent plane, and we are looking for the intersection, we are looking for the points x, y, which satisfy this is equal to 0 and also this one is equal to 0. So we have this set, and this is a linear problem, and yeah, we can write it that way. That's a standard form. Then we can rewrite that in the matrix formulation, and then we find this solution, and in this case this is the solution, and then we update by adding, okay, here, and this has to do with x minus 1. We need to add 1 to get the real x, and we need to add, for y we need to add 2 to get the real y. And so this is the perfect explanation why Newton for systems works in the way I told you. Okay? And so this was this chapter, this last thing, to really understand the mathematical reason, what's really the idea behind Newton's method. And for me, this is a wonderful, great explanation. And I miss that in many textbooks about numerics. I think this is the best explanation you can get.